We physicists have waited 100 years since 1916 for this photograph. It is a region where black holes might just be one of the most fascinating and mysterious phenomena in the universe. They are massive beasts in terms of power, but, at the same time, virtually invisible to us. A black hole might weigh perhaps 2 to 4 million times the mass of the Sun. However, due to the research put into them over the last couple of decades, we have gone from knowing absolutely nothing about them to learning more up close and personal. And well, things have just gotten crazier. Michio Kaku just announced that we've finally gotten a look at what's inside a black hole, and this new information sheds light on details the world of science might have missed all along. Join us as we dig deeper into black holes and unveil what's inside space's big bag. Before we get into the details of what Michio Kaku found, we have to talk about the firsts. Even though most of us have some idea of what black holes are, there are still gaps in the right information. In 1916, Albert Einstein published his theory of general relativity, which predicted the existence of black holes. At that time, the concept of black holes was purely theoretical. It took another 50 years for the scientific community to find evidence that black holes actually exist. This happened in the 1960s, when they were studying the Cygnus constellation and noticed an oddly bright blue star emitting X-rays. This star wasn't a stagnant object, but was orbiting around a giant black something. Further investigation revealed that the X-rays weren't just moving on their own, they were being sucked into the black object they were orbiting. Thus, the name black hole. This discovery was significant because it provided proof that black holes actually exist and were not just a figment of Albert Einstein's wild imagination. While that was great, it also meant that there was this unreal entity in space that we urgently needed to know more about. So, researchers all around the world got to work. This black hole was named Cygnus X1, located in the Cygnus constellation about 6,000 light-years from Earth. It was no small discovery. It's about 14 times brighter than the Sun and incredibly dense, which gives it a strong gravitational pull. The pull is so strong that not even light can escape it, which is why it's called a black hole. The concept of a black hole is both fascinating and terrifying. It is a region of space where gravity is so strong that nothing, not even light, can escape. Anything that gets too close to a black hole will be pulled into it, never to be seen again. But that aspect of danger makes it even more necessary to learn everything there is to know about them. Was this it, or were we just beginning? The answer ended up being the latter. After the discovery of Cygnus X1, scientists began searching for other black holes. They found that there may be over 100 million black holes in the Milky Way alone. But because they are incredibly hard to detect, we still don't have an exact number. Nevertheless, from the looks of it, there are several million black holes in the Milky Way, in our very own galaxy, which makes them even more important to study. The main concern with black holes is always going to be gravity. Their gravitational pull is so intense that anything that enters gets compressed down astronomically until it becomes a singularity. In simpler terms, black holes are like cosmic vacuum cleaners that suck everything in. One of the scariest parts about researching black holes is the fact that if someone were to fall into one, they would get stretched to the point of becoming a single line. This process happens slowly, and the person would die before reaching the final form. So, let's just say no one should step into one. But they're everywhere, so could we be in danger? Despite the fact that the closest black hole to Earth is 1,500 light-years away, it's still close enough to raise questions and concerns. In 2021, scientists released the first clear photograph of a black hole, specifically the M87 black hole. This black hole was photographed over several nights, and with each photograph, researchers gathered more and more evidence about it. They stitched the individual photos together to fill in the gaps, and in doing so, they figured out that black holes have 3 layers. It's not just one single gaping hole of nothingness, as many believe. Things are much more complicated than that. To get to the nothingness part of a black hole, you must first pass through 2 layers. The first layer is called the event horizon, which is the point of no return. Once you pass the event horizon, you will be sucked into the black hole. It only gets worse from there. The second layer is the photon sphere, the region where light orbits the black hole. Any light entering this region is trapped and cannot escape the black hole's gravitational pull. Finally, there is the third layer, the singularity. This is where everything that enters the black hole gets compressed down astronomically into a singularity. The singularity is a point in spacetime where the laws of physics, as we know them, break down. At the singularity, density becomes infinite, and the laws of physics cease to exist. What makes this infinitely worse is that every black hole you study will be different from the last. Sure, they follow the same three-layer concept, but they function differently. If this were any other phenomenon, we'd just use telescopes to study it in detail. But black holes can't be studied like that. Scientists must observe them indirectly by studying the radiation they emit and the gas and dust surrounding them. Sending a probe inside is impossible because it would be crushed before reaching the singularity. Because of this, scientists can only study black holes in a two-dimensional way, even though they are three-dimensional phenomena. To complicate things, every black hole is unique, and the laws of physics break down when we try to explore their insides. Traditional scientific inquiry doesn't apply. Despite these challenges, there are many compelling theories about the formation of black holes. One suggests that they are created from collapsed stars. When a star exhausts its fuel, it can no longer produce energy to counteract gravity, and the star collapses in on itself. If the star is massive enough, it will continue collapsing until it becomes a singularity. To better understand black holes, NASA scientists turned their attention to the core of galaxy M87. They observed a whirlpool of superheated hydrogen gas spinning at an astonishing rate. Scientists deduced that a colossal mass, likely a black hole, must be at the center of this galaxy to prevent it from flying apart. In 1963, mathematician Roy Kerr used Einstein's equations of gravity to describe a spinning black hole. Kerr's solution predicted that instead of collapsing into a point, a spinning black hole would form a ring of fire or a thin disk called the ergosphere. This region is where the laws of physics begin to break down. Kerr's model also predicted the existence of an Einstein-Rosen bridge, also known as a wormhole. This theoretical passage through spacetime connects two distant regions of the universe, or even parallel universes. In Einstein's theory, space and time are interconnected, forming a four-dimensional fabric called spacetime. Objects with mass warp this fabric, creating a gravitational field. Imagine a sheet of paper with 2 points on it. Drawing a line between them represents how objects move through spacetime. But what if you could fold the paper in half, creating a shortcut? This is the idea behind a wormhole, a shortcut through spacetime. Although no one has observed one directly, wormholes are predicted by general relativity. However, they are inherently unstable and would collapse almost immediately. Despite this instability, the concept of wormholes and black holes as pathways to other parts of the universe or even different times has intrigued physicists for decades. Could we use a wormhole for interstellar travel or time travel? Probably not, but the idea remains fascinating. Roy Kerr's solution for spinning black holes suggests they might connect to different regions of the universe, or even different times. However, critics argue that while Einstein's equations explain gravity, they don't address the quantum forces governing radiation and subatomic particles. To fully understand black holes and wormholes, we need a theory that unites gravity with quantum theory, a theory of everything. The most promising candidate is superstring theory, which proposes that subatomic particles are tiny, vibrating strings. The universe, according to this theory, is like a symphony of these strings, which can explain gravity, black holes, and other cosmic phenomena. Superstring theory, however, requires 10 dimensions of spacetime, far beyond the 3 dimensions of space and 1 dimension of time we experience daily. These extra dimensions might be curled up so tightly that we can't observe them directly, but they could still affect our universe. The mathematics of superstring theory is incredibly complex, but many physicists believe it will eventually solve the problem of quantum black holes. Recent breakthroughs suggest that string theory could describe quantum black holes, but only in 2 dimensions, not 10. Even so, solving this in higher dimensions could lead to revolutionary discoveries about the universe. In conclusion, black holes are fascinating, terrifying, and still largely mysterious. From Einstein's predictions to Kerr's wormhole theory and the possibilities offered by superstring theory, they challenge our understanding of physics and the universe. Could we one day travel through black holes or harness their power? Only time and research will tell. Until then, the mysteries of black holes remain some of the most compelling puzzles in science. If you liked this video, please give it a thumbs up, and we'll see you in the next one.